All right, this is the quiz that you guys took after your multiple choice quiz in class on Friday. So this is the free response section, and I have 4 forms, A, B, C, D. I'm going to go over each of them one at a time, starting with this one, which is Form A. If you want to skip ahead to any of the other forms, you can see the video description, and you should be able to click on those timestamps to jump ahead to look at Form B, C, or D if you'd prefer to start there. Number 1 says a 3-meter long string sustains the standing wave when attached to a heavy block as shown. The wave speed is 100 meters per second. What is the frequency of the wave pictured? So what we're going to need to do in order for us to be able to solve for frequency, we need to know the velocity of the wave, which is in the question, 100 meters per second, along with the wavelength of the wave, which is not in the question. Yes, I know there is a length, 3 meters long. But that is the length of this entire string. This entire string contains more than one wave, and so that is not your wavelength. You need to figure out how many waves are on this string so that you can figure out the wavelength. So if we're counting the waves through one full wave cycle to the next point in phase, it'd be right there. So this is one full wave and then half more. So this is 1.5 waves. So if 1.5 waves is 3 meters long, how long is 1 wave? Well, all you have to do is 3 divided by 1.5, which of course is going to be 2 meters. And so the wavelength that you're going to substitute into this equation will be 2 meters, not 3, because this again is not the wavelength, it's the total length. So you do need to figure out how long 1 wave is. I know 3 meters is 1.5 waves. So again, that's just a quick division step. The other thing we have that we can substitute in is the velocity. It is in the question, 100 meters per second. You do want to make sure that your units are in meters per second for your velocity and in meters for your wavelength. And we're good there. So we can go ahead and solve. And when we do that, our frequency will be in units of hertz because it will be in units of inverse seconds. The meters are going to cancel and you're going to have just over S. And so that's the same thing as a hertz. But anyway, if you want to solve for frequency, again, you have this 100 equals 2F. And so F obviously has to equal 50. I'm getting that by dividing both sides by 2. And then you have that your frequency is equal to 50. And then that's the abbreviation for hertz, Hz. So that is the frequency of the wave pictured. Letter B says calculate the lowest possible frequency for a standing wave in this string, and it's even giving you a nice little hint here and reminding you that the lowest frequency is called the first harmonic or the fundamental frequency. As a reminder, your harmonics are all multiples of the fundamental. So this up here is the third harmonic, which you need to know in order to answer this next question. So if the third harmonic is 50 hertz, then the fundamental frequency or the first harmonic would be 50 divided by 3 because again, they're all multiples of that first harmonic. And so you can get a calculator out if you don't want to do this one in your head and do 50 divided by 3. And so your fundamental frequency would be 16.66 repeating, or 16.67 hertz. And so that means that if this is the fundamental or your first harmonic, the second harmonic would be that times 2, the third harmonic is this times 3, which is this, and so on and so forth. It's the same pattern that we learned about in the notes on Thursday. Letter C says point X is labeled in the diagram above. What is the name given to this point? What type of interference produces point X? And explain your answer in complete sentences. So point X is right here. The name for this point on a standing wave is called a node. The nodes are actually all of these points that I've actually labeled already, plus this one at the end. So the third harmonic, which is what is pictured here, has a total of 4 nodes. A node is the name given to the point, and it is produced by destructive interference. Okay, so your node is going to be produced by destructive interference, and that means that there are, again, in the background, you can't see it. This isn't animated like the ones in the notes, so you might want to go back and look at the notes slides so you can see them in motion. But all that means is that these points on the wave don't move. And the reason that they're not moving is that a standing wave is produced by a wave and its reflection. And when that wave and its reflection interfere with each other, there are portions that cancel each other out, causing them not to move at all. Those are your nodes. And then there are portions that have a lot of oscillation up and down, where you see these bulges right here and where you have your highest amplitude, your crests and your troughs. That's not what this question's asking about, but those points are called antinodes, and they're formed by constructive interference where your waves are adding together. Okay, so again, node is produced by destructive interference. If you wanted to add to that to explain it, you could say these are the points on a standing wave that do not move, and they are stationary because of this right here, because of this destructive interference where everything is canceling out, causing it to be motionless. All right. This is the last question on Form A. It says 3 students are asked to propose one change to the setup that would cause the speed of the wave and the string to increase so the wave travels faster. Their responses are below. Beneath each statement, circle whether you agree or disagree with the student and explain. So we've got 3 statements here from Penelope, Quentin, and Raphael. Penelope says increasing the tension in the string changes the medium and produces a faster wave. That I'm going to agree with. Again, the speed of a wave is determined by the medium, and changing the tension is one thing that we can do to change the medium. Specifically, increasing tension does increase the speed of the wave. It was something we talked about in class. We saw it a couple different times in the slides, and it was in one of the video clips that I showed you yesterday. And so you would want to explain that here, that the speed of a wave is determined by the medium, and that increasing tension does in fact change the medium and would in fact make it move faster. Over here it says, Quentin says, increasing the frequency of the oscillation in the string would cause the wave to move faster. And this is one of the common misconceptions. Frequency and wave velocity are not the same thing. And again, if you were going to explain why you disagree with this statement, you would need to reiterate what we said over here. The velocity of a wave is determined by the medium. So changing the frequency doesn't change the velocity. All that does is affect the wavelength. But the velocity would remain the same unless you also changed the medium. And again, you could say that here. And that's going to apply here as well. Increasing the amplitude of the string oscillation would cause the wave to move faster. Again, I'm going to disagree with that. Amplitude affects the energy of the wave, its ability to do work, but it does not affect the speed with which it moves. Again, that is determined by the medium and only the medium. All right, so again, you would need to explain those, but that is what you should have selected for those 3 statements on Form A. All right, this is Form B. Form B says a 3-meter long string sustains the standing wave when attached to a heavy block as shown. It's the exact same question, except the picture looks a little bit different this time. It says the wave speed is 48 meters per second, so that part's different as well. But otherwise, this is going to be the same solution that we did for Part A. Again, we can solve for wave frequency if we know the wave velocity and the wavelength, because this is our wave equation. Wave velocity equals wavelength multiplied by frequency. The wave velocity is in the question. It is 48 meters per second. Again, double check your units, but those are the ones I want. And then I need the wavelength. And yes, I know there is a length in the question, but this is not a wavelength. Again, wavelength is the length of one wave. This is not one wave. This is 1, 2.5 waves. Okay, so this picture shows a total of 2.5 waves. If 2.5 waves are 3 meters long, then we can figure out how long one wave is by simply dividing 3 by 2.5. And so you would do 3 divided by 2.5, and you would get your wavelength to be 1.2. So each of those waves is 1.2 meters long. Again, that is the appropriate unit. You do want meters. And so now that we have these things, we have 48 equals 1.2 times f. We can solve for f. Again, to solve for f, we're going to divide both sides by 1.2. So we have 48 divided by 1.2, giving us 40. So the frequency of the wave pictured is 40 hertz. Question B says, calculate the lowest possible frequency for a standing wave in this string, and it even gives you a nice hint and says this is the first harmonic. Again, as a reminder, the harmonics are all multiples of that first harmonic, that fundamental frequency. This up here, not the first harmonic. Okay, this wave has a frequency of 40 hertz, but it can be less. We can get the first harmonic. This is the 1, 2, 3, 4, 5th harmonic. Okay, so again, you would need to know what harmonic you're looking at up here in order to use that information to help you answer here. So the 5th harmonic has a frequency of 40 hertz. That means the fundamental frequency, or the first harmonic, would be 40 divided by 5. Okay, because again, each of them is a multiple of that fundamental. Again, 40 divided by 5 is 8 hertz. So the fundamental frequency of this wave is 8 hertz. That means the second harmonic would be 16, the third harmonic would be 24, the fourth harmonic would be 32, and so on and so forth. Fifth harmonic, of course, 40. But they're all multiples of the fundamental frequency, which in this case is 8 hertz. Question C says, point X is labeled in the diagram above. What is the name given to this point? Point X is right here, and it is labeling one of these troughs, one of these areas of oscillation. And when we look at standing waves, we have points on the wave in the middle that have names, and we have points that are oscillating up and down. And that's what we're being asked about here. Those points that oscillate up and down are called antinodes. And so point X is an example of an antinode. What type of interference produces that? Well, antinodes, where you have these maximum amplitudes, where you have your crests and your troughs and you have the oscillation up and down, are produced by constructive interference. And so you'd want to say that. I know this question isn't asking about these other points, these right here. But if it were, those are points that don't move at all, and they don't move because everything cancels out. Those points, these nodes, are caused by destructive interference. So again, you can add to this. Antinodes, they're produced by constructive interference, where the wave and its reflection add up to give us these great amplitudes where we have our crests and our troughs, or something like that, because that's what's happening with a standing wave. It's produced by a wave and its reflection interfering in the same medium when they overlap, and areas where they overlap in the same direction is where you get this constructive interference. It's where you get your troughs, it's where you get your crests, and then you have these other points on your wave that don't appear to move at all. They appear to be stationary, and that's because of the canceling out due to destructive interference. All right, this is the back of Form B. It says, 3 points are labeled on a wave, P, Q, and R, that is propagating to the right towards a wall. The arrow shows the direction in which wave P will move in the next instant. Which direction will point Q move in the next instant? Explain using complete sentences. Okay, so again, as this wave propagates, I want you to remember we had this in our slides and our notes, and we said that points like P and Q and R, these are not points that you want to think of like roller coaster cars moving on a track. It's not going to go up and over the hills and down and all of that. Rather, the points of the medium are in simple harmonic motion, where you have oscillation that is either up and down or oscillation that is back and forth. You should recognize by looking at this diagram that you're looking at a transverse wave. And when you look at a transverse wave, the particles of the medium move in a direction that is perpendicular to the wave propagation. Here's my direction of propagation. It's to the right-hand side. And so if I'm answering a question about which direction these particles are going to move, your only choices are up and down, because it needs to be at a 90-degree angle. Okay, it needs to be perpendicular. And so the wave is going this way. Here's my wave. Okay, that's your wave velocity. And so your oscillation's perpendicular to that because this is a transverse wave. And what's happening is you need to picture this wave, pretend it's moving in your head, and that wave is moving through these points. And so like this crest right here, it's going to end up over here in a moment. This trough right here is going to end up over here in a moment. This crest is going to end up over here in a moment. Everything is going to shift to the right, and when it does, that's why this moves down, because this point is going to end up over here in a moment. P is going to be down here. Okay, but the question's not asking about P, it's asking about Q, and point Q, in the next moment, this point that's up here is going to be over here in the next moment, and so Q is going to move up. Okay, again, this is a little bit easier to see if I could make it move, which is what you have in the notes slideshow. So I would recommend in going back to look at the question. This basically exact same question is in there, but you need to picture this thing moving through it. If this crest is going to end up over here, that means Q is going to be oscillating up and down, but it's obviously going to have to be moving up. Okay, so Q will move up in the next instant as the wave passes through. You definitely want to make note of the fact that Q can only move up or down due to the fact that this is a transverse wave and the direction of the medium is going to oscillate in a direction perpendicular to the wave's velocity. All right, again, I didn't write it out, but that's what you want to do when you write it out. This is Form C. Form C says a 5-meter long string sustains the standing wave when attached to a heavy block as shown. The wave speed is 52 meters per second. What is the frequency of the wave pictured? Again, it's the same question that we've answered already in Form A and Form B. It just has different numbers. And so if we take a look at it, again, if we want to find wave frequency, we can go back to the wave equation. The velocity of a wave is equal to its wavelength times its frequency, and we can use this formula to solve for F. But that means we need to know both V and lambda. We need the velocity and the wavelength. Well, the velocity is the speed. It's right here, 52 meters per second. So we are going to be substituting that in for our wave velocity. That is the appropriate unit. You do want those velocities in meters per second. Wavelengths we want in meters, which I do have a distance in meters in this question, but that's not a wavelength. That is the total length of this string, 5 meters long. And this string contains more than one wave. So again, you need to figure out how many waves are in this string. If you're counting them, one wave would go right there. That's 1 and then a half. So I have 1.5 waves. If 1.5 waves is 5 meters long, how long is one wave? Well, you're just going to divide 5 by 1.5, and that'll tell you how long one wave is, which is 3.3 repeating. And so the wavelength we're going to use is 3.3 meters. And so that's our substitution step. We would say 52 equals 3.33 times F. And if I want to solve for F, I'm going to divide both sides by 3.33. So 52 divided by that answer, and there is my frequency, 15.6. My unit for frequency is hertz. All right, that is A. Looking at question B, it says calculate the lowest possible frequency for a standing wave in this string. We're being asked to find the first harmonic. Again, the harmonics are all multiples of the fundamental frequency. They're all multiples of some basic lowest harmonic, the first harmonic. And so you need to figure out what harmonic you're looking at here, because this is not the first harmonic. Again, you can count these bulges. 1, 2, 3. This is the third harmonic. And so if the third harmonic has a frequency of 15.6, we can figure out the first harmonic because it will be 1/3 that much. So we're going to take our answer and we are going to divide it by 3. And that is your first harmonic or fundamental frequency, is that 15.6 divided by 3, which is equal to 5.2 hertz. And so that just means that all of your overtones, all of your other harmonics are multiples of this. So this is your first harmonic, your second harmonic would be 10.4, your third harmonic would be 15.6, your fourth harmonic, you'd add this again, or 5.2 times 4. And so again, that's how you're going to answer questions like that. All right, letter C says the point X is labeled in the diagram above. What is the name given to this point and what type of interference produces point X? So point X is right here. It is showing us this point kind of in the middle along that equilibrium line if you were to sketch it in. And there are several points like this on this wave. Those right there. Those are called nodes. Okay, so the name given to that point is a node. What type of interference produces it? It is produced by destructive interference. Again, when we're looking at standing waves, this standing wave is the result of a wave and its reflection interfering with each other. There are portions of the wave that move a lot, where you see these crests and these troughs. Those portions have a different name. They're called antinodes, and they are produced by constructive interference. But we're asked about this point. These points in the center of the wave, they actually appear stationary. They don't move at all, and the reason they don't move at all is because of destructive interference. The wave and its reflection cancel each other out, meaning that you don't end up with any displacement, you don't end up with any oscillation, and you have these points that appear to be standing still. So you can explain that here for answer choice C, or rather for question C. All right, here is the last part of form C, which is number 2 on the back. It says 3 points are labeled on a wave, P, Q, and R, that is propagating to the left towards a wall. The arrow shows the direction in which point P will move in the next instant. Which direction will Q move in the next instant? Explain using complete sentences. So first things first, you need to look at this wave and you need to recognize that this is a transverse wave. I know it's a transverse wave because I see this pattern of crests and troughs. And I also know that when I have a transverse wave, the direction of the particle oscillation, because all the particles in any type of wave are in simple harmonic motion, they're vibrating back and forth, and that means either left and right or up and down, depending on the type of wave you have. But with the transverse wave, by definition, the direction of your particle motion in your medium is perpendicular to the direction of your wave propagation. The wave is propagating or moving to the left, and so if I want my, if I want to examine the movement of these particles, they can only move up or down, because that's what they're going to be doing, back and forth, up and down, over and over again, because my wave velocity is this way, again, perpendicular, that's the definition. Okay, so your answer for the which direction Q will move is either up or down. Don't tell me anything else. These are not cars moving on a roller coaster track. It's not going to climb up this hill and then ride down and all of that. Point Q doesn't move sideways. The wave instead moves through it. And what that means is, like this point on the wave, for example, is going to be over here in a minute because the velocity is that way. This point on the wave, for example, is going to be over here in a minute, and wouldn't you look at that? That's where point Q is. So if the trough is going to end up over here, that means point Q is going to be down here at that point in time. That's the direction the medium has to move in order for this wave to pass through it. And so your answer to the question is that Q has to move down. Okay, this is again really easy to see if you look at it animated in the slideshow, because I have this question in there. Different wording and slightly, but the same basic idea. So go back and look at the notes if you're still confused. But the answer to this, which direction will point Q move in the next instant, is Q will move down. When you explain this, you need to talk about the fact that the wave passes through it and that the particles are oscillating in simple harmonic motion. And you probably should mention that this is a transverse wave. And so the particle oscillation needs to be perpendicular to the direction of wave propagation, meaning it can only be up or down because it needs to be 90 degrees from the direction of the velocity of the wave. All right, last one. Here is Form D. Form D says a 4-meter long string sustains the standing wave when attached to a heavy block as shown. The wave speed is 20 meters per second. What is the frequency of the wave pictured? Again, all of these questions are basically the same with slightly different numbers to them, and the picture is a little bit different than Form C that we just looked at. But otherwise, it's the same process. If I want to solve for the frequency of a wave, I can use the wave equation, and I know that the velocity of the wave is equal to its wavelength times frequency. The velocity is in the question. It's right here. It's the same thing as the speed of the wave, and it's 20 meters per second. The wavelength of the wave, though, is not in the question. Yes, I know that there is a length in the question. This is not your wavelength. This is the total length of this whole thing. And that whole thing is more than one wave. How many waves is it? 1, 2.5. 2.5 waves are 4 meters long. How long is one wave? I can get that by dividing. So we're going to do 4 divided by 2.5. And we're going to get 1.6 right there. And so that's our wavelength. So if I want to find my frequency, I'm just going to plug these numbers in. And I need to divide both sides by 1.6. So 20 divided by 1.6 is going to give me my frequency as 12.5 hertz. All right, part B. Calculate the lowest possible frequency for a standing wave in this string. And it's asking you specifically for the first harmonic. Again, the harmonics are multiples of the fundamental frequency, okay, or the first harmonic. So this right here, not the first harmonic. First things first, we need to figure out what this is. 1, 2, 3, 4, 5. This is the fifth harmonic. And so if the fifth harmonic has a frequency of 12.5 hertz, then I can solve for the frequency of the first harmonic because it will be 1/5 that amount, 12.5 divided by 5. And so we'll go back to the calculator, divide by 5, and there you go. The frequency is 2.5 hertz. All this means is that the first harmonic or fundamental frequency is 2.5 hertz. The second harmonic would be 5. The third harmonic would be 7.5. The fourth harmonic would be 10, and so on and so forth. Fifth harmonic, 12.5. They're all multiples of that value. All right, so that's B. All right, question C. Point X is labeled in the diagram above. Here it is, right there. What is the name given to this point, and what type of interference produces point X? All right, so point X is on one of the troughs. It's on one of the areas of the standing wave where you have maximum oscillation, where you have this up and down motion, and you see these bulges in that standing wave and these areas where you have maximum amplitude. Those areas are called antinodes, and they are produced by constructive interference. Okay, so as a reminder, a standing wave is the result of a wave and its reflection interfering in the same medium. So you have a wave propagating through this string, and then it's reflecting back on itself. And when it does that, it overlaps with itself. And there are portions of the overlap where things build, and you get this constructive interference, this resonance, and you get these areas of maximum oscillation like point X and antinode. But there are also these points that appear to be stationary. Those points are called nodes, and they are formed by destructive interference. Okay, and that's not what this question's asking, but just so you know. All right, so antinodes, they're created by constructive interference. This is where crests overlap with crests or troughs overlap with troughs, and it gives you this area of maximum amplitude where they're building on each other. Okay, back, last question. Okay, this is part D. It says 3 students are asked to propose one change to the setup that would cause the speed of the wave on the string to increase so that the wave travels faster. Their responses are below. Beneath each statement, circle whether you agree or disagree with the student and explain. And we have 3 students, Penelope, Quentin, and Raphael. And let's read their statements. Penelope says increasing the amplitude of the string oscillation would cause the wave to move faster, and I have to disagree with Penelope because amplitude only affects the energy of the wave. We talked about the fact that the energy is directly proportional. Sorry. There, I was like drawing the symbol wrong. All right, is directly proportional to the amplitude squared. Okay, so energy is directly proportional to amplitude squared. And so the amplitude does affect the energy, but it does not affect the velocity with which it moves. It affects its ability to do work, sure, its potential. Okay, and so this is a statement I disagree with. In fact, the only factor that affects the velocity of the wave is the medium itself. So the only way we're going to get a wave that travels faster is if we change the medium. So you should say something like that down here. Quinton's statement says increasing the tension in the string changes the medium and produces a faster wave. I have to agree with that. That's what we just said a second ago. The only way that you can cause the wave speed to change is if you change the medium. Changing tension is a way that you can do that. Specifically, increasing tension will increase velocity. And so you can say that down here. Increasing the tension will increase the velocity. It changes the medium, whatever you want to add. The last statement says increasing the frequency of the oscillation in the string would cause the wave to move faster, and I have to disagree with Raphael. Increasing the frequency of the wave does not change the wave's velocity. Again, the velocity is determined by the medium. The only thing that would be affected by me changing the wave's frequency is its wavelength, because it would, they're inversely proportional to each other. But in my explanation, I would say something along the lines of the fact that the medium determines wave speed, and I have not changed the medium, and therefore I would not be changing the speed of the wave. All right, guys, that is it for this free response quiz. So hopefully that clears up any questions you may have had. It's going to be kind of similar to the question that you see in your free response portion of your test on Tuesday.